Hello, my name is Aaron Waters, and I'm a senior software engineer with the Flatiron Institute in New York City with the Simons Foundation. This talk describes how WebGL2 makes it possible to use the GPU of a standard computer to do highly parallel computations. By making use of a feature called transform feedback, a programmer can capture the outputs from a GPU computation and either send them into a traditional GPU processing stage, another one, or extract the data for other uses. This talk describes support libraries I built, which simplify the process of building transform feedback processing stages, and how transform feedback stages can be created and controlled from within a Jupyter notebook. The talk describes an implementation of the marching Tetrahedra method for generating three-dimensional isosurfaces from dense arrays as a concrete example of the marching tetrahedra of transform feedback. The marching tetrahedra method is implemented in two feedback stages that I will be showing you. So let me share my screen now. And I will start my talk. All right, first off, I'd like to thank some people. I always run out of time and forget to thank people, so I want to thank people up front. I have a lot of collaborators that I've worked with at the Simons Foundation who inspired me to build these things and also helped me debug them and offered suggestions. And also I have an intern, Ms. Luo, who helped me with this presentation. And I've had a lot of help from the Jupyter community, particularly the Jupyter widgets community, and notably Jason Grout and Martin Brettles, and also people like Brian Granger, UV Panda, and many others. And also I've been inspired by three.js, which is a WebGL library that's available in JavaScript. It's an amazing piece of software, which I will be talking about here. All right, so let's talk about use cases for transform feedback. This is the biggest use case, which is a viewer for three-dimensional matrices. So you have a three-dimensional matrices of values, which represent something. In this case, they represent the density of inside a human body as determined by MRI processing. So first we get the matrix, then we load the matrix into the widget. And that's all you have to do. And then you have a view of the widget, and you can rotate the view and you can change the intensity level. So here we have the skin. If we go back a little bit, we get back to the bones. And then in addition to that, we can focus in to some part that we're interested in, like the spine. And we can rotate that around or zoom in a little closer, rotate it in, and look and see what the spine looks like. This data was derived from MRI data from the National Institute of Health, and I subsampled it down so that it was a little bit smaller. You can do larger arrays, but the performance begins to get jumpier. And so that's the basic use case. How is this implemented? So let's talk a little bit more about. So just to review. To use the widget, you need a matrix. In this case, I'm creating a matrix, which is just a very simple matrix where every entry has the distance to the center of the matrix. So what does that give you when you view it in the viewer? It gives you a bunch of spheres. So here, if we go down here, we have a sphere. We rotate it around. And if we go up, the sphere begins to intersect the edges of the matrix, so you have a truncated sphere. The various components here, this is a three.js view. This is a three.js view. These three slices in the X, Y, and Z dimensions are canvases, HTML5 canvases, and they're built using something called JPDoodle, which is a library I built. So let's talk about what the components are. With the top level component we were looking at is in a module called Volume. Volume uses a module, the surface rendering module, and the surface rendering module uses WebGL3 for presentation and a module called Feedback, which implements the HTML5 or the WebGL2 feedback mechanism I'm talking about today. And then, of course, those are both based in WebGL2, which is the underlying functionality. The object itself is a widget, which is built using something called JP Proxy Widget, which is a helper module I built, and which is built on top of widgets, which again is a part of Jupyter, which of course uses other features of HTML5. And I'm also drawing the X, Y, and Z slices are drawn using something called JPDoodle, which uses Canvas 2D. So that's sort of a 10,000-foot view of where things fit together. Now, let's talk about what the basic WebGL. So what I'm talking about is today is transform feedback in WebGL2, which is built on top of basic WebGL. So what is basic WebGL? It's an amazing library which allows a programmer to do things like 3D modeling in a web browser. And there are two, it has a standard pipeline, and the standard pipeline, the input to the standard pipeline is usually usually a collection of triangles. These go into something called a Vertex Shader, which does things like move the vertices of the triangles to different positions, or sometimes decides colors and normals and things like that, can do a lot of different computations. That goes into some components that you're not allowed to change. And ultimately, it enters something called a fragment shader, which decides on the color for each individual pixel of each triangle, and then that gets output to the screen. Now, we're mainly interested here in the Vertex Shader because that's the part that we can access using the feedback mechanism. A very simple Vertex shader is shown here. All it does is a couple matrix. It takes an input vector and two input vectors, actually, and multiplies them by two matrices, basically. That's not very interesting from a mathematical point of view. The interesting thing from a computer science point of view is that you can send in literally tens of millions of vertices into the processing pipeline, and this Vertex shader will process them all in parallel, roughly speaking, on thousands of processors instantaneously. So you can do things like take a complex geometric figure and rotate it in real time, as I've already demonstrated with the widget I showed you. So, for example, if you wanted to represent a chimpanzee, the first thing you need to do is find triangles which represent the surface of the chimpanzee. That's called a mesh. And then you take the mesh. So you take the chimpanzee, divide it into triangles, and then you load all those triangles into the GPU, and then you run the rendering pipeline with appropriate shader programs. And the Vertex processing stage will broadcast your rotation matrix to all the vertices of the chimpanzee in parallel, and it looks like this. So you have a single matrix which is shared by all processes, and then millions of vertices down here, millions of processing, millions or thousands of processors handle each of the vertices in sequence, and out come millions of rotated vertices. And then if you want to change the rotation, what you do is you change the matrix and leave everything else alone, tell the processing pipeline to run again, and you've got a new rotated chimp. Now, if you want to There's also a feature of WebGL that I use, which is called instancing. And for instancing, you don't want one chimp. You want thousands or millions of chimps that are all described by the same mesh, by the same vertices. And in this case, you can describe the mesh once. And so the mesh is just, the vertices of the mesh are along the top here. And then you can change the position of each. So you can specify the position for each chimp separately along a separate dimension, and then have the any common attributes like the matrix broadcast. So here we have each processing element gets one vertex from the mesh, one position from the position array, and the common matrix combines them into a rotated, translated vertex and produces an output. And this is all done very quickly. In my case, I don't want to generate chimps, but what I want to generate is isosurfaces. And the way that works is you take the voxels of the matrix. Each voxel is broken into 6 tetrahedra with 2 triangles each, with 3 vertices in each triangle. And so, here we have the corners of each voxel along the vertical dimension, and then along the horizontal dimension is all the triangles it gets divided into. So that's the outer look. That's how it looks in a so that's how the isosurface maps into the instancing model. Now let's talk a little bit about how feedback works. Okay, transform feedback is the idea that, so for example, I have a method which produces isosurfaces. I don't want to have to write a program which there are libraries out there like three.js which are very good at presenting triangles once you have them. So I know how to get the triangles, but once I have the triangles, I don't want to have to figure out how to color each individual pixel. I want to use three.js, which is a library to do that. And the way you can do that is you put something in the front of the processing pipeline. So here I'm going to stick something in the front which is the isosurface triangle generation. And then the triangles, and that runs on the GPU. And when it's done, it feeds all the triangles into the standard pipeline that's created by three.js in order to produce the result and the final result that's displayed. So the way it looks is, it looks a lot like a standard Vertex shader. You have uniforms, vertex attributes, instance attributes, and a shader. That produces some output, but we can capture that output, call it feedback output 1, and then we can send that output into the next processing stage. So here we have the output from the previous processing stage being fed in as instance attributes to the next processing stage, and that will produce feedback output 2, which can go into the standard processing pipeline, or it could go into a third stage, potentially. It can go into many different stages. And the name feedback comes from the idea that you can actually take the output of the feedback and feed it back into itself. And that will allow you to implement things like particle systems. Now, feedback, to program this, it's actually quite difficult if you use the direct libraries provided by OpenGL. So what I've done is I have created something called the feed WebGL wrapper library, which does all the standard things in a standard order. For example, here's the run function, which I'm not going to talk about in detail, but basically it does a bunch of operations that you always want to do in the same order for every run. Basically it captures the basic underlying operations. The underlying operations are very much like programming a state machine or an assembly language program. This is a little bit more higher level. It groups things into objects, and objects which can be linked together. And but it doesn't try to come up with a new paradigm. It lives within the same paradigm, but it's just a slightly higher level. Gets rid of the boilerplate code that you tend to need to use when you write feedback programs. So I'm going to look at a trivial example now. So the trivial example looks like this. We have a single vector, a three-dimensional vector called shift, and then a whole bunch of input vectors. And we want to send it into a shader program, which produces the input vector plus the shift as an output. And I'm going to use a very simple shader program to implement it. And then in order to get the wrapper library to run this program, what you need to do is you need to specify what the variables are and how they are linked to data inputs and outputs. So here's the program. The program says, okay, there's an input vertex and there is a shift vertex and there's an output vertex. And what I want you to do is add the input vertex to the shift vertex and produce an output vertex. So that's the program. Very stupid program it's a standard hello world example. Now we need to link this to values. So first, the shift factor is a shared value. So in this case, I'm going to here the value is going to be -1, 0, and 1. And this chunk of code here says, oh, shift vector is a uniform, and here's its value when you link the program together. Now the input vertex is not a single vertex. It's actually an array of vertices. And the array of vertices comes from a buffer. So we declare the buffer down here. And then up here we say, oh, the input vertex variable is an input variable. And it comes from, it should be bound to the buffer that's called the input vertices buffer. So that's how you link things together. And finally, the output vertex is specified in this chunk of code. Oh, the output vertex is a feedback output, and it has 3 components each. So basically, you need to tell the system what the variables are and how they are linked to data sources in a declarative manner. And it runs like this. We import the module. We say, okay, basically we build and compile the program, and then we run the program, and then we get the feedback outputs back. Now, what is 0 to 4? Well, 0 to 4 is 1, 2, 3 plus -1, 0, 1. Now, once we've got the program on the GPU and it's all compiled, we can run it again. So let's run it again. We're going to change the value of the shift vector to 300, 200, 100. And then we will run it again. And then, so we get 301, 201 as the next level. So, of course, this is a totally artificial example. It's much slower than using NumPy to do the same thing, of course, because there's so much overhead. But if we had 30 million vectors, it might be faster. And in particular, it might be faster if the operation we were implementing was much more complicated, which it generally is. So just very quickly, I'm going to talk about how to use this system for a more complex problem, which is the isosurface generation. So again, just to review, to generate an isosurface, you start with an array, and what you want to do is convert it to a bunch of triangles that look like this. Here are the triangles. And actually, you want to produce triangles and normals, which are so here's a diagram which shows that each triangle has a normal vector sticking out of it. Those are the little arrows coming out of the triangles. Those are used for coloration. All right. In order to do this, the way it's done with marching tetrahedra, which is a very simple method conceptually, is you take each voxel. Here we have a voxel with 2 negative values and 6 or 3, 4, 5, 6 positive values. And what we want to do is find triangles which cut between them at the 0 threshold interpolation. What you do is for the voxel, you divide the voxel into 6 tetrahedra, and then for each tetrahedron, you decide, does it have 2 above the threshold and 2 below the threshold, in which case you use 2 triangles, or does it have 1 above and 3 below, or 3 below, or 3 above and 1 below, in which case you use 1 triangle. And that's how you determine the triangles, except that there's another case, which is all of them are either above or below the threshold, in which case there's 0 triangles. You go through all the voxels and you produce those triangles, and that produces your isosurface. So that's the basic idea. How is that implemented as a transform feedback pipeline? All right, so once again, we have an array. We want to produce a bunch of triangles like that. So we need to break down the steps for producing the normal vectors and the triangles. Okay, first of all, on the GPU, you identify the voxels, the corners in the array, which contain some piece of the isosurface. And you do that by looking at the corners and seeing if it has 1 corner above and 1 corner below, then it contains some piece of the isosurface. So that looks like this. You send in you send in the threshold value, you send in the corners of each voxel, you test to see if there is a crossing, and you return the corners and an indicator saying 1 or 0, is it crossing or not? Now, at the next stage, so the output of the test stage is the filled voxels have some piece of the isosurface inside them. So in the next stage, which is actually implemented in JavaScript, you throw away everything except the interesting voxels. And that usually throws away almost all the voxels. And that's a very important optimization step right there. And then finally, you apply the method I described, the marching tetrahedra, to each of the remaining voxels. And that produces the triangles. And that's the basic steps. So there are basically 2 steps. You identify the voxels, you generate the tetrahedra. Once you generate the tetrahedra, you get a bunch of triangles, and then you send it into the standard pipeline. So that's the basic sequence of steps. All right. Now, summary and conclusions. So I've described something called WebGL2 feedback, which implements highly parallel computations. It doesn't implement an arbitrary computation because you have to have something which has very few inputs, or few inputs and very few outputs, and that there's no communications needed between processing elements. At least in a given stage, you can communicate at the next. You can feed back into the next stage, and the next stage can see what the previous stage did. But you can't you can't communicate within the same stage. So it looks like each processor sees something that looks like this. There are uniforms, and textures are interesting. There are a small number of arrays which can be large, so you can send in a large amount of data, but it has to be only in the form of arrays. And so each processor sees a bunch of uniforms and arrays, and possibly instance attributes, definitely vertex attributes, and it produces some sort of feedback which gets captured by some downstream processing. The overall architecture at the GPU level looks like this. You have the vertex, you have many vertex attributes and many instance attributes that get broadcast, or that get sent to individual processing elements, and then the shared parameters are broadcast to the processing elements, and then it produces a matrix array of outputs. A lot of operations look like this, and the obvious one would be something like a particle simulation or isosurface generation, like I've demonstrated. But I am now at 36 minutes, so I think I will stop and thank you very much. And I'm delighted to have given this presentation. I'd like to thank the organizers and all the people who helped me out with this work. Thank you so much.